Okay, so there's often a question, I'll ask, raise your hand please if you've ever had to jump a car that has a bad battery. Okay, did you know that there's procedures on how you're supposed to connect up those cables so you don't blow anything up? Okay, a lot of times people just go in and start connecting things up randomly, but there are procedures that you should do that. I always take the red terminal of the jumper cable, connect it to the good terminal of the battery, the good battery, I connect up the red. And then before I connect up the black terminal there, I don't want to have a complete circuit yet, so I put the red jumper on the good terminal of the battery. And then I take the other side of that cable and I connect the red to the red terminal of the bad battery. I don't have a complete circuit yet. My goal is not to have a complete circuit until everything's safe. So I put red on red, red on red. Then what I do is I'll take the black cable, the negative cable of the good on the good battery, and I'll connect it to the negative terminal. On the other side, the bad battery, I will take that black cable and I'll either connect it to the negative terminal or I'll connect it to the chassis of the car. And the reason for that is some people know that the negative terminal of the battery is usually connected electrically to the chassis of the car. You aware of that? And the reason for that is that we ground everything to the car's body. At the back side of the car, if you're putting in trailer lights, you don't have to run a cable from that light bulb all the way back to the battery of the car, because you just connect it to the frame of the car, and that serves as your connection point. So it's a convenient thing, but it also puts everything at the battery's terminal, sort of connected to it. So the question would always be, if it's really difficult to jump a car battery, you need to have a good battery, by the way, around you to be able to jump that battery. Why not just take two 9-volt batteries and keep these things in your glove box and connect them in such a way that you can get 18 volts, and just keep this handy so that in the event that your car battery dies on you, you don't need jumper cables, anything. You just take these things over there and you could just jump the car battery by taking these two 9-volt batteries. I'll show you how to connect this up here really quick. Every battery has two terminals on it. One's a negative terminal, one's a positive terminal. So that side, the bigger of those terminals is the negative, the smaller of those terminals is the positive. And so I could just take these two and connect them like this. And if I were to take them and connect them like so, then what I've got is I've got 18 volts of potential. So now on this terminal, that terminal right there is the positive terminal. This is the negative terminal. And it's like two 9-volt batteries connected together. I get 18 volts. So the question is why not just keep that in the glove box, and when your battery dies, just take those two 9-volts and just use that to jump your car? And why is this, Jacob? It won't work. Why not? Say it again?
There's like 0.
It's not 0, but it's actually really small. And so the idea behind this is that even though it's 18 volts of potential and the car battery is only 12 volts, its ability to deliver current is very, very low. And the reason for that is it doesn't have a really high chemical reaction rate. So those of you that have taken chemistry or will take chemistry, the rate of reaction is really small here. So this provides a very small rate of, and it really is a chemical reaction. So what's providing the energy here is a chemical reaction. And because there's not many chemicals inside that battery, I ask it to go, it can't deliver a lot of current. It's just limited in its supply. So the 12-volt car battery, it's like opening up a faucet, right? So let me show you just as a water analogy. You might remember when I used this thing, one of these streams was a really large stream coming out, the other was a trickle. Well, if I had the two 9-volt batteries connected together, I might be able to get like a little bit of a stream going out of that to be able to try to run that car, but it just doesn't simply have enough, it doesn't have enough current capacity. Whereas I open up the floodgates on the 12-volt thing, and it's just a huge rush of current. Raise your hand if you've ever had to go and buy a new battery for your car, and there's like 5 different batteries they show you. They always try to sell you the highest price one, but what are the different ratings for a battery that would be important? If you ever, raise your hand if you've ever bought a car battery, you had to go and buy a car battery on your own. A few people have. How much does it cost?
I just get the cheapest one. I don't know how much it costs.
Okay. You can get by with the cheapest one for a little while. So I had to buy a battery last year for my car, and the guy tells me, well, you should get this platinum one. It costs $240. You can get this other one, $180. But I'm like, well, let's see, $60 is it worth it? You know how they would rate that? They would say this one has 510 cold crank amps. You know what that means when they say it's a cold crank amp? Your battery's going to fail most likely when it's cold outside. If your battery's weak, it's not going to work when it gets 20 degrees out. And the reason for that is when it's cold, the rate of chemical reaction is really low based on temperature. So you ask it to start the car and it just can't do it. It's like your lights will like dim a little bit. You hear this clicking noise. Click, 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 click. Raise your hand. Have you ever heard it? Yeah, it happens. The problem is that the cold crank amps is not very high. So when you go and buy this new battery, it's like, hey, this platinum battery, it'll provide 510 cold crank amps. So what that means is you say go, it will deliver 510 coulombs per second of charge. I mean, that's huge. It's like opening floodgates. And when it's cold out and you have a weak battery, you ask it to go, it needs 500 amps to be able to start the car's starter, but it can only deliver 300 amps. It's not starting. So it really has to do with how quickly it can deliver that energy. So it's really about the power. Power is the rate at which we do work. Electrically, that rate can be found by multiplying the current and the voltage. So I'm going to zoom in a little bit so you can see it better. Power, again, goes back to mechanical ideas. It's how quickly work is being done. If I take the current that's being delivered and multiply it by the voltage that's being supplied, I would get the amount of power being delivered. Now, I want to do a quick unit analysis for you. So I want to refresh your memory. Mechanical power, we talked about the watt, was equal to 1 joule of energy per second of time. So we say 1 joule per second. When I say something is a 100-watt light bulb, that means 100 joules of energy every second. Okay, now, I want to show you how we can look at the units of this power is equal to I times V. Let me show you. I'm going to switch the color. We said that for electricity, it's I times V. Well, I is measured in amperes, but the ampere is the coulomb per second. So the very first unit there for I is a coulomb per second. 510 amps, it's 510 coulombs per second of charge delivery. The voltage is also thought of as a joule per coulomb. So that car battery might provide 12 joules of energy for every coulomb of charge. If I multiply those together, coulomb per second times joule per coulomb, those of you that are math savvy would see that the coulombs reduce out, and what I get is the joule per second, which is exactly the unit for power. So how I get power from electricity is I take how much current I'm getting, so many amperes, multiply it by what voltage I'm sort of running that at. That's how you get power. So the problem with the 9-volt batteries is not that they don't have enough voltage, they just can't supply enough current. So it's really the fact that these things have small rates of reaction. It really has to do with that. Now, I like to use mechanical analogies wherever possible. It's hard to see electrons moving through systems, but we understand water flow pretty well. Here we have 3 different waterfalls, all falling from the same height. We might say that all of them have the same voltage, if you wanted to think of that from an electricity standpoint. They all fall through the same height. But the one that's going to deliver the most power is the one that has the highest flow rate. If I were to take a turbine, like a generator, and place that here as a spinning kind of agent to be able to harness the energy of that water, the one that's going to develop the most power would be this one. It's just simply because it's got the most current. Now, I could also look at it from a standpoint of same flow rates but different heights. So when I looked on that thing called Google Images, I don't know if you've ever used that search engine before, but I looked for waterfalls that had the same flow rate, and that's what I was trying to find here, is that the flow rate is the same, but this one being from a higher height would be able to do more work. And so in this case, the higher voltage with the same amount of current. So again, voltage times current. Now, I would like to show you guys how to calculate a few things with power. There are 3 different equations that we can use for power. One of them is your standard, I times V. I want to show you how you could change one of these 2 values using that relationship to be able to develop another equation. So let me write the 3. P is equal to I times V is one equation that I could use for calculating power. It's probably the most basic. What I'm going to do is I'm going to replace one of these 2 things with its relationship up here. So I'm going to take, let's take the I. Let's take the I of this equation and replace it with V over R. Now, I'm going to use some color coding so you guys can see that better. I'm replacing the I with V divided by R. So when I do that mathematically, then I can get to an equation that says power could also be V squared divided by R. I could find the power being delivered by taking how much voltage I have being applied, square it, divided by the resistance of the device. Okay, I'm going to show you one more. 3. I can take power is equal to I times V, and now what I'm going to do is I'm going to replace the V here. Give me some good colors here. All right. Equal to, gosh, you've got to be kidding me. Okay, so I'm going to keep the I. Now I'm going to replace V with its relationship up here. So I'm going to replace the V with that. And that would become I times R. And I get power is equal to I squared times R. A little bit of mathematical manipulation there to be able to get 3 equations for power. Sometimes I know the current and the voltage. I multiply them, I get power. Sometimes I only know how much voltage I'm being supplied, and I know the resistance of the device, so I use V squared over R. Sometimes I know how much current I have flowing through it, but I don't know the voltage. I do know the resistance, so I just take I squared times R. I have 3 ways in which I can calculate power. If I know 2 of those, I can find the power. Now, I want to go through and show you a few examples. I'm not going to be able to do all of them because we're limited with time. An electric space heater, raise your hand if you've ever used one. Maybe down in the basement, you don't have enough heating, or maybe the ductwork is not sufficient to be able to keep that back bedroom warm, so you plug in an electric space heater. The electric space heater takes a very high amount of electrical current to run. You look at the power rating. I have these instruments out, these appliances out, so you can see how to find the power rating for a particular appliance or device. They're always stamped with a certain rating. You take this thing, you plug it into a wall outlet, and I might be interested in knowing the resistance of that heater. So you've got that plugs into a 120 volt outlet. So you've got these things on the wall. You plug that in, there's some cabling that goes in, you've got this huge, inside of this, there's basically just a huge resistor that when you plug into that thing, it just runs electrical current through that resistor. It warms up, it glows. You might have a fan there to be able to blow some of the air out, but it's just basically a big resistive element. I wanted to calculate how much resistance is there. So let's see, the voltage that's being supplied is 120 volts. The power is 1320 watts. So, my gosh, that's a really powerful appliance. Lots of current is going to flow. In this case, it's just asking for the resistance. So I'd like to know how big that R value is. Well, I would use this version of the equation. I would say power is equal to V squared divided by R, because I know the voltage and I know the power and I'm looking for the resistance. So usually making a list of the things that I know and the things I don't know helps you identify an equation. So R here would be equal to V squared divided by the power. And so I take 120 volts squared, I'm going to divide that by 1320, and I get about 11 ohms. And I'm going to trust that you could plug those numbers into an equation and get that. The resistance of that device would be about 11 ohms. And I really could. If I were so inclined, I could take the plug of that electric heater and just hook it up to a VOM meter, and I could measure that resistance just using that. It'd be really low resistance because I want a floodgate of water flowing through that charge flowing through it. Small electronic device rated for 1/4 watt, draws a current of 35 milliamps. I'd like to know the device's internal resistance. So again, I might do something like this. Power is equal to 0.25 watts. I have a current flow of 0.035 amperes. I'm going to pause for a moment, make sure that I have to pay attention to the SI units. So 35 milliamps, I have to put that in amperes. And I want to know the resistance. So I'm looking for R. Well, I look at my equation list and I see that this equation relates P, I, and R, and I have enough there to be able to solve for R. Making a list often helps me identify what equation is useful. So R here would be equal to P over I squared. I've got 25 or 0.25 watts. I divide that by 0.035 squared, and I have a resistance that I can calculate. 0.25 divided by 0.035 squared. That's about 204 ohms. So that particular device, resistance of about 204 ohms. Okay, last one. I'm not going to do number 4 with you because of constraints of time. I would like to give you a moment to see if you can figure out how to answer number 3. Today's 4K televisions, if you look at the back side of those TVs, they'll say, it's a 350 watt TV. And so any appliance, anything that you plug into a wall outlet is required to have a stamp on it that says this is the rating for it. So you look in the back, 350 watt TV. A 4K TV dealer might be out there and saying, hey, I want to have these TVs on display. How many TVs could he plug into this branch circuit? Those outlets are all connected to a panel, and that panel provides 15 amps of service to those outlets. Anything more than that is going to trip the breaker. So the question might be, how many of those TVs could you have plugged in and not get over 15 amps? I'm going to see if you guys can figure out a way to go through that. Give you a minute, see what you can do. Okay, number 3, try it. If you're watching this from home, you should pause the video and try that. All right, they're about ready to report back to me here. If you're watching this video from home, hopefully you've had enough time to figure out how to do that. Anyone have a number? And you can't see them. I don't have the camera on. Oh, there's a few people. Yeah, would you mind sharing? What'd you come up with? If you got it wrong, that's okay. This is a safe area. But what'd you come up with? 5 TVs. You got it right. I'm going to show you how you could do this. So some people are able to do this pretty well. Other people might struggle with it. I'm going to determine the power available. So I'm just going to determine how much energy or how much power I have available by taking the fact that I have a maximum amount of current of 15 amps, and that current is being delivered from a 120 volt service. And so I'm just going to say, well, what is my service voltage and what's the maximum amount of current. If I have 15 amperes of current available and it's 120 volt service, that tells me that I have 1800 watts available to be able to drive various things. That I could look at my panel that's in my basement, and if it's a 20 amp breaker, I can determine how many things I can have plugged in without overcurrenting that device using this equation. If I have 1800 watts available, the next part's really easy. I divide that by 350 watts per TV, and you get 5.1 TVs. Now, obviously, you can't put in a 0.1 TV. If you put in 5, you're going to be under the 15 amps. If you put in 6, it's going to try to draw more current than is available, and it will trip that breaker. So it provides you a way to sort of manage that. Okay. Nice job. All right. I'm not going to do number 4 with you. Again, power is not going to be heavily assessed on here, but it is. There are some practical things for you. Last thing I want to look at with you guys. This is the last topic for today. Hopefully you have a chance to be able to look at a few problems on your own. As a matter of fact, I think I might pause the video here. So if you have to watch this thing from home, I don't want the video to be 45 minutes, so I'm going to stop this. That's the bulk of the things here. But we got to talk about this thing about electrical energy and power. So I'm going to stop sharing, and then hopefully if you have to watch this thing, you'll have to see me about how to deal with this particular quantity.